Hi everyone, happy Wednesday. All right, so we are journeying into skill 6. Last I saw you on Monday, we talked about horizontal asymptotes, and that was our introduction into the different types of characteristics that rational functions may have when we graph them. Pardon me. So we saw this chart, and there were 3 different situations that we're going to come across in relation to identifying if a horizontal asymptote exists, and if it does, how to find it. We also saw 3 different examples on what a rational function graph could look like. But keep in mind, these aren't the only 3. Okay, it's up to us to find all of the appropriate characteristics and then analyze what the function's doing in relation to those. And as I mentioned on Monday, we will start to graph on Friday when I see you guys in the classroom. Now we're just going to kind of play around with the characteristics, see what they are, how to find them, and so forth. So the first one is our vertical asymptote. Okay, the vertical asymptote is always written as x equals some number, not a hashtag, it's a number. And think about your axis of symmetry, right? It's a vertical dashed line. Our vertical asymptotes are the exact same thing. They're a vertical dashed line, so they need an equation. These are referred to as non-removable discontinuities. Discontinuity is where the function doesn't exist. It's discontinuous. It doesn't exist there. Non-removable means that the function will never, ever, ever, ever exist there. And why? Because the vertical asymptote is where a function is undefined. Okay, the graph will not cross this asymptote, and that's because the function is undefined there. Okay, I'm actually going to switch colors real quick so that it's not the same. Okay, so our vertical asymptote comes from where the function is undefined. It will not cross it. So think about, if I'm a rational function and I am a fraction, where is the function undefined? Dun, da, da, at the denominator. So how to find it? We set the denominator equal to 0. Set the denominator equal to 0 and solve for restricted values. Again, why? Because we cannot have a fraction with a denominator that's equal to 0. So in order to find where the vertical asymptotes exist, we're looking for the restrictions. Think back to skill 1, we found the restrictions. Some of you asked, why are we doing this? Valid question. We did it for skill 4 for solving, and now for our vertical asymptotes. Okay, so there's one of our characteristics we'll need to search for. Another one is our horizontal asymptotes. The purpose of these is to guide the end behavior. And we saw this in the investigation that we did the day before Thanksgiving break. Pardon me. Its purpose, there's my yellow, is that it's going to describe the end behavior of the function, meaning the graph can cross the asymptote. Vertical asymptotes, you can't cross them. Horizontal, you can. Their purpose is to guide or describe the end behavior. And let's go ahead and put in guide there so we can remember that. How to find them, see the chart above. Because last class on Monday, we spent time filling that chart in, filling in the gaps, and playing around with them. Okay, so look back at that chart for your horizontal asymptotes. The third type of asymptote that we might come across is the oblique. All right, oblique could be slant. It could be parabolic. There's a bunch of different options. For us, these are going to be, oh my golly, sorry everyone. These are going to be slanted lines. Okay, again, they could be parabolic, they could be cubic, it all depends. But for us in this course, we're only going to see oblique asymptotes that are slanted lines. These also guide the end behavior of the function. Okay, so that means oh my gosh, come on. That means that just like the horizontal asymptote, it's going to describe the end behavior, muy importante, when it is not horizontal. What does that mean? You will not have a horizontal and an oblique asymptote at the same time. You will not have a horizontal asymptote and an oblique asymptote on the same graph. They do not coexist. Why? Well, because of where they come from, and we'll talk about that in a second, but also because their purpose is to guide the end behavior. If you have an oblique and a horizontal asymptote, your function's confused. Where does it go to the left and to the right of the graph? Do I go to the horizontal asymptote? Do I go to the oblique? I don't know. Okay, so they will not coexist on the same graph. Now, how to find them? These exist when the degree of the degree of the numerator is 1 larger than the degree of the denominator. Okay, so it's when the degree of the numerator is 1 larger than the degree of the denominator. Of the denominator. And remember, a rational function is written like a fraction. Fractions are division. So if they exist, how do we find them? We're going to take the numerator divided by the denominator. So we're going to divide the numerator by the denominator to find the equation of the oblique asymptote. All right, 3 possible asymptotes. Vertical asymptotes we do not cross. They come from the restricted values that make the denominator equal to 0. Horizontal and oblique asymptotes guide the end behavior of the function, and they will not ever coexist. The next characteristic that we'll need to be able to find and identify are holes. These are removable discontinuities. So they are places where the function doesn't exist, but it doesn't mean it can't exist there. Let that sink in for a second. So holes are described as removable discontinuities, meaning the factor that is creating the discontinuity can be removed or canceled. So the factor creating the discontinuity can be removed or canceled out. Here's how we find it. A hole exists if there is a common factor in the numerator and the denominator that can be canceled out. So if there is a common factor in the numerator and denominator that can be canceled out, in order to find a hole, we're going to need to find the x and the y coordinates. So if you cancel out a factor, you need to solve the factor to find x. So basically, we're looking for the root. And then you need to plug the x value into the simplified equation to find the corresponding y. And we'll do examples of all of this. So right now what we're doing is we're organizing our chart for us to refer back to when we're on our own and we're practicing finding the characteristics. Okay, 2 more. X-intercepts. Remember, x-intercepts are points on the x-axis, meaning they have coordinates of x, 0. So they are found by setting y equals to 0 and solving for x. But think about what we're dealing with. These are fractions. So which part of the function would need to equal 0 for the y value to equal 0? Well, think about it. If we have y, and this is just an example, y is equal to 3x minus 1 all over 2x plus 5. Okay, so we set y equal to 0, and we're trying to solve for x, but oh golly, I've got an x in the numerator and the denominator. So how do we get how do we get x out of the denominator? We're going to have to multiply both sides by the denominator. I can't solve for x if it's in the numerator and the denominator, so we're going to multiply both sides by the denominator. Oh shoot, what's happening on the left-hand side? Yes, 0 is equal to 3x minus 1. So in order to find the x-intercept, all we need to do is set the numerator equal to 0 and solve. Why? Because of the example I just showed on the left-hand side, the denominator is going to cancel out. So set the numerator equal to 0 and solve for x. Okay, for the last one, our y-intercepts. Remember that y-intercepts are points on the y-axis, meaning that the coordinate is 0, y. So we're going to set x equal to 0 and solve for y. Whew! All right, everyone. Holy guacamole. So these are all of our characteristics that we're going to need to find. And I'm going to jump into skill 7. We aren't going to graph, but we're going to play around a little bit finding the characteristics so that you get some practice and you see the order in which we need to find these. Okay, so let's take a look at example 11a. Again, we're jumping to skill 7 just to find the characteristics, not to graph. The first thing that you want to do is factor. Always. Write that down. You need to factor first because we need to see if there is a common factor in the numerator and the denominator that we can reduce, that we can cancel out. You only want to factor the quadratic or factor out a GCF or maybe even factor a cubic if it's one of our factoring patterns. So looking at example 11a, the numerator doesn't have a GCF that's going to be helpful. It doesn't have a factoring pattern that's going to be helpful. So I'm just going to leave it as is, negative 2x squared plus 1. Now in the denominator, I see that both terms have a GCF of 2x squared. So I pull out the 2x squared, leaving me with x plus 2. Now that we've factored, if you're thinking, oh yes, cancel the 2x squareds, stop the urge, because the numerator is one factor, and I can't take from one piece if I don't take from both. So in this case, we don't have any common factors, which leads me to my first characteristic. You must always factor first to see if there is a common factor to be canceled, giving us our whole. So for this particular rational function, there isn't a whole, so we're going to put a whole, none. The next thing we want to look for, and there is a reason why I'm going in this order, if you have a whole, every other characteristic that you find must come from the simplified equation. Every characteristic that you find must come from the simplified equation. I can't stress that enough. If you need to, pause this video, write that down. Okay, so since we don't have a whole, the next thing I'm going to look for are any vertical asymptotes. They come from the denominator. So I'm going to take each factor in my denominator, starting with 2x squared, and then followed by x plus 2, and set them equal to 0. Because remember, your vertical asymptotes come from the restricted values, what makes the denominator equal to 0. All right, well, for the first one, I'm going to divide by 2, giving me a vertical asymptote at x equals 0. For the second one, I'm going to subtract 2, so we get x is equal to negative 2. Notice I'm listing them both individually because they're each individual lines, so I need to show that. I'm also going to highlight them because once we get to graphing, there's going to be a lot of work, and we need to make sure that we can easily find what we're graphing. Okay, next comes our horizontal asymptote. Well, for the horizontal asymptote, we have to look at the degrees. Here, I'm going to go back to the original. What's the degree of the numerator? Yep, it's 2. What's the degree of the denominator? Hopefully you said 3. It's always, if we're in standard form, the highest exponent. If we are in factored form, we're counting the number of x's. All right, so since, looking back at your chart, since the degree of the numerator is greater than that of the denominator, yep, that is going to be the situation where we get a horizontal asymptote at y equals 0. Again, highlighting so I can easily find it. Well, since I have a horizontal asymptote, I know that I don't have an oblique asymptote. I also know that because the degree of the numerator is smaller than that of the denominator. In order for me to have an oblique asymptote, I'm going to have, yep, the degree of the numerator 1 greater than that of the denominator. Okay, next comes our x-intercepts coming from the numerator. So I'm going to take negative 2x squared plus 1 and set it equal to 0. And then I'm going to solve. So we get negative 2x squared is equal to negative 1. X squared is equal to 1/2. So x is going to be plus and minus the square root of 1 over 2, which is plus and minus the square root of 2 over 2 if I rationalize. All right, so writing that in coordinate form, because we must always, I'm going to have plus and minus rad 2 over 2, comma 0. We will have to graph this, so on Friday, we'll put it into a decimal approximation. But for now, this is good. All right, last but not least for our characteristics, we need to find the y-intercept. So I'm going to plug in 0 for all of my x's. I get negative 2, and just like we looked at for the horizontal, you can use the original given or you can use the factored form. So I'm going to go back to the original. Negative 2 times 0 squared plus 1 all over 2 times 0 cubed plus 4 times 0. What happens in the denominator? Well, the numerator gives us 0 plus 1, and then, we are undefined. So, ladies and gentlemen, we put none for the y-intercept. So there are all the characteristics for example 11a. Think back. First, we factored. Then we looked for the whole. Then we found from top to bottom of our chart. So really the only order that we went out of was to find the whole first. Okay, let's take a look at 11b. Oh yeah, here the numerator is already factored for us, but notice the denominator is not. So just like I always do, I'm going to use the x method. A times c goes to the top, so negative 6 with negative 5 at the bottom. Figuring out what multiplies to negative 6 but adds to negative 5, I'm going to go with negative 6 and positive 1. All right, with the x method, we then plug that into or substitute that into our middle value. And then we're going to factor by grouping. So I'm going to group the first two terms and the last two looking for the GCF. 2x squared and 6x has a GCF of 2x, leaving us with x minus 3. And then x and negative 3. Well, they only have a GCF of 1, which may sound weird, but we still have to pull something out of the two terms. And it finally factors to x minus 3 times 2x plus 1. Alrighty. So in the numerator, we have 3x times x minus 1 all over x minus 3 times 2x plus 1. I'm going to put this in a thought bubble because I can to show that that's where I factored. And looking, I don't see any, common factors from our numerator and our denominator. So once again, I'm going to state that there are no wholes. Oopsies, that's not how we did it. We did it like this. Whole, and then we put none. Okay, so going from top to bottom of our handy-dandy chart, the next thing we need to find are the vertical asymptotes. Again, they come from the denominator setting each factor equal to 0. We need to know what values are going to make our function undefined. The first is x equals 3. So we know we're going to have a vertical asymptote at x equals 3. And I'm going to, oh, not yet. And then the second one, I got excited and ahead of myself. I'm going to subtract 1, divide by 2. So we see that we have 2 vertical asymptotes. And here we go. I'm going to highlight so that when we get to graphing on Friday, I can find it a little bit easier. Next on our list is the horizontal asymptote to see if we have one. Using the chart we filled out on Monday, let's write the degree. Well, the degree of the numerator, we've got 2 x's, and it's in factored form, so the degree is 2. Hey, the degree of the denominator is also 2. It is in standard form, so we take the highest exponent. Since the degrees are the same, we need to look at the leading coefficients for our horizontal asymptote. It's going to be at y is equal to 3/2 or 1.5. Again, highlighting that. Now we have a horizontal asymptote, which means we will not have an oblique. We can also see that because the degrees are the same. In order to have an oblique asymptote, the degree of the numerator must be 1 larger than that of the denominator. Okay, next is our x-intercept characteristic, which means we're going to have to look at the numerator. I'm going to set 3x times x minus 1 equal to 0. And thanks to that zero product property, I can set both of these factors equal to 0, giving me an x-intercept of 0 and 1. I don't know why I had that in parentheses. Well, wonders never cease. And we have to make sure that we write our x-intercepts as coordinates. So we have 0, 0, and 1, 0. Again, highlighting this will be super important for us later. Dun, 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 dun. Last but not least, we have our y-intercepts. Okay, so setting our x's to 0, we have 3 times 0 times 0 minus 1 all over 0 minus 3 times 2 times 0 plus 1. And again, you can use the original form of the equation or the one that we factored out. They're the same function. This gives us 0 times negative 1 in the numerator, and then negative 3 times 1, ultimately giving us 0, 0 yet again. Yay! Nice work, everyone. All right, I'm going to do one more with us just for the purpose of practice. We'll finish the other 2 examples. I'm going to skip C for right now. We'll finish the other 2 examples with their characteristics on Friday. Okay, so looking at D, so yes, we'll do C and E together on Friday. Looking at D, oh my golly, I see we can factor the numerator because it is a difference of squares. So we have x plus 2 times x minus 2 all over x plus 2, remembering that we always factor first to see just this. Can we reduce a factor from the numerator and the denominator? And yes, we can. So we're left with x minus 2. This is the equation that we are going to use to find every other characteristic from here on out. Okay, this is, I don't know why this is such a big decision. This is the characteristic that, oh, golly. This is the equation that we're going to use from here on out. You should write this down if you're going to forget. Once we cancel a factor, 2 things happen. Number 1, we have a whole. Number 2, the original equation no longer matters. Okay, we're now using the simplified form. So let's identify the whole first. Okay, the whole is going to be written in coordinate form. So in order to find the x, I'm going to take the canceled factor, which is x plus 2, and set it equal to 0, giving us an x coordinate of negative 2. Okay, in order to find the corresponding y value, I'm now going to take negative 2 and substitute it into the simplified form of the equation, giving us negative 4. So our whole is at negative 2, negative 4. And I'm going to highlight it so I don't forget. Okay, now looking at our simplified equation of x minus 2, what is that? Yeah, it's a linear function. It's a line. Do lines have vertical asymptotes? I sure hope you said no. Do lines have horizontal asymptotes? Nope. Do they have oblique asymptotes? Nope. make sure, and this is an excellent example of how we really have to analyze what we're graphing. It's not cookie cutter parabolic. Yeah, it's not cookie cutter, ooh, fun little cubic. We find the characteristics first by factoring the function, identifying if there is a whole or not. In other words, is there a common factor in the numerator and the denominator? Oh no, shush. There we go. And then finding the characteristics using the chart from top to bottom. So since this is a line, yep, there aren't any asymptotes, but there is an x-intercept, most likely. So if I set x minus 2 equal to 0, we see that it's x equals 2. Where did I get x minus 2? It's the simplified equation. All right, so we're just going to algebraically solve for the x-intercept, and we'll do the same for the y-intercept. I'm going to set 0 equal to x minus 2. Did I just do that? I sure did. Erase. There we go. I'm going to take y is equal to 0 minus 2. For those of you that caught that error, nice job. So our y-intercept is 0, negative 2. Again, I'm going to highlight that so that when we graph it on Friday, we know. All right, everyone. If you want to, you can go ahead and try to find the characteristics for E. I think that would be a great opportunity. For C, I suggest we wait. We're going to see a characteristic we definitely need to walk through together. So go ahead and attempt Skill 6 homework. I will see y'all on Wednesday. It is Wednesday. I'll see y'all on Friday. Have a fantastic day.